Hello Year 12 and welcome to Purple Mountain Maths. We're doing the 2024 HSC paper for Maths Advanced. This is part 10, question 29, 30 and 31, worth 13 marks. Question 29. Consider the curve y equals ax squared plus bx plus c, where a is not 0. At a particular point, the tangent and normal to the curve are given by t of x equals 2x plus 3 and n of x equals minus a half x minus 2 respectively. The curve has a minimum turning point at x equals minus 4. Find the values of a, b and c. Pause here to try yourself. Okay, so let's get started. Straight away I notice it's a parabola. I don't know the value of a, so I don't know if it's concave up or concave down. It could be either, but I do know it's a parabola. And I know that there's a particular point where the tangent and normal are given by those lines. I'm going to call that point P. So let's go ahead and find the point P where the tangent and the normal meet. So I'm going to set them equal to each other. So t of x equals n of x at P. So let's go ahead and figure out where that is. 2x plus 3 equals minus a half x minus 2. So 2.5x equals minus 2 minus 3, which is minus 5. So that's 5 on 2x equals minus 5. So x equals minus 2. Let's find the corresponding y value. If x equals minus 2, then t at minus 2 equals minus 4 plus 3 equals minus 1. So point P is minus 2 minus 1. That's helpful. Okay, we're told that the minimum turning point is at x equals minus 4. Let's think about what we know about minimum turning points. They just reveal to us that the curve is concave up, and that minimum turning point occurs on the axis of symmetry. X at the axis of symmetry is minus b on 2a, and that equals minus 4. So minus b equals minus 8a, or b equals 8a. That's going to be useful to us. We also know that the turning point is where the first derivative equals 0. So given y equals ax squared plus bx plus c, then y dash is 2ax plus b, and we know that that is 0 at x equals minus 4. So 2 times a times minus 4 plus b equals 0. And that's just another way of getting us to the same place, the fact that b equals 8a. All right, let's look at what else we know. The tangent has slope equals 2. So at x equals minus 2, we know that y dash equals 2. So 2 equals 2a minus 2 plus b. And we'll get 2 equals minus 4a. Let's now use equation 1, however we arrived at that. And so we'll get 4a equals 2, or a equals a half. Putting 2 into 1, we'll get b is 8 times that. So b equals 4. And finally, we know that minus 2 minus 1 fits on the parabola. So minus 1 equals a x squared plus b x plus c. So minus 1 equals 2 minus 8 plus c. Minus 1 equals minus 6 plus c. I get c equals 5. So they're my answers. A is a half, B is 4, C is 5. Question 30. Suppose the geometric series x plus x squared plus x cubed and so on has a limiting sum s. By considering the graph y equals -1 over x minus 1, or otherwise, find the range of possible values of s. Pause here to try yourself. Okay, so let's look at what we know about this geometric series. I can see that each time I multiply by x, so I can see that a equals x, I can see that r equals x, and I know it has a limiting sum. So there exists a limiting sum that implies that the absolute value of r must be less than 1. And I know that the infinite sum is given by a over 1 minus r, which in this case means it's x over 1 minus x, provided x is less than 1. All right, so they're inviting us to consider that graph. Let me build that up. So let's first of all consider what a regular hyperbola looks like. I know what that looks like. It's that shape. Now consider what happens as I nudge it to the right by replacing x with x minus 1. Now we're talking about that one. Now consider what happens as I put a minus sign in there. So now I'm flipping it in the x-axis. So it's still pushed over by 1, but I'm actually talking about this hyperbola. And if I was to nudge that down by -1, which is the graph they're asking me to actually consider, I've got an asymptote at 1, I've got an asymptote at -1, and I've got this shape going on. So that's helpful. So I can see what the shape is that I'm considering. Notice a few things as well with that. At x equals 0, y equals -1, -1 on 0, -1, -1 plus 1 equals 0. So I actually know as it goes right through 0, 0, which is helpful. All right, so this graph which they've asked me to consider, -1, -1 on x minus 1, if I tidy that up so I can use it, it's minus x minus 1 minus 1. So it is minus x on x minus 1, or the same as x over 1 minus x. So that is in fact the infinite sum I've been asked to consider. So what do we know about limitations on that? Well, I know for a start that x absolute value has to be less than 1. Or in other words, x is trapped between -1 and 1. And I know that at x equals -1, that function would be -1 minus 1 over -1 minus 1, which is -1 plus a half is minus a half. So I can see that at x equals -1, I must have a value of minus a half. So let's zoom in on that function, which I drew before. So I know it goes through the origin. I know that there are asymptotes there and there, which are at 1 and -1. And I now know that when x equals -1, which is as low as it goes, at x equals -1, it goes through minus a half. So that point there is -1 minus a half. All right. And for x is more than that, it's going through the origin and then it is approaching that asymptote. So we actually do have a constraint on s, because s only applies for x in that range, then we can say that the infinite sum is going to be bigger than minus a half. And that's my answer. Question 31. Two circles have the same centre O. The smallest circle has a radius of 1 centimetre, while the largest circle has radius 1 plus x. The circles enclose a region QRST, which is subtended by an angle theta at O as shaded. The area of QRST is A in square centimetres, where A is a constant and A is positive. Let P be the perimeter of QRST. By finding expressions for the area and perimeter of QRST, show that P of x equals 2x on 2a over x. Pause here to try yourself. All right, with these questions, I always like to consider the smaller radius as little r and the bigger radius as capital R. So in this particular case, I can see that the little radius I've been given is 1 and the big radius I've been given is 1 plus x. I have a glance at what I'm being asked to do. P of x equals 2x plus 2a on x. And the first thing I notice about that is I notice it doesn't involve theta. So I'm going to need to write my expressions just involving x, and if I initially have an expression involving theta, I'm going to need to rearrange it so it's all just about x. Okay, so let's recall what the perimeter would be by first principles. So the perimeter is whatever the length is of that big arc, the outside arc from Q to R, plus it's the length from R to S, plus it's the length from S to T, and plus it's the length from T to Q. All right, so the length of an arc is theta times the radius. So theta times the radius is the outside arc. This one I'm provided as x. This one is theta times 1, and this one is x. So let's tidy that up. We get 2 theta plus 2x plus theta x. I can factorise on the theta if I want to. Theta 2 plus x plus 2x. So that's part 1. I also have information about the area. I know that the area A is defined as the area of the big sector minus the area of the smaller sector. So let me calculate that. That's a half of r squared theta less a half of r squared theta. Factorise on a half of theta. It'll be outside of 1 plus 2x plus x squared less that 1. So the area is a half theta 2x plus x squared. All right, so let's make theta the subject of this equation. Theta equals 2 times a over 2x plus x squared. And let's now put 2 into 1. So putting 2 back up into 1, I'm going to get that the perimeter is theta, which I now know is this, outside of 2 plus x plus 2x. Put all of that like that. 2a, there's another 2 plus x plus 2x. I've got an x on the bottom there. That cancels. I get 2a on x plus 2x, or writing the other way around. I've got 2x plus 2a on x, and that is as required. Okay, part B. Show that if the perimeter P of x is minimised, then theta must be less than 2. All right, so thinking about minimising P, they're inviting us to differentiate. The minimum implies that P dash of X equals 0, so let's go ahead and do that. Remember, P of X equals 2x plus 2a x to the minus 1. So P dash of X equals 2 plus minus 2a x to the minus 2. That looks like 2 minus 2a on x squared. Okay, so if P dash of X equals 0, then 2 minus 2a on x squared equals 0, or 2x squared minus 2a equals 0. So x squared equals a. X could be plus or minus root a, but obviously a is positive by context and x is positive by context. So a is just the positive, x is just the positive root of a. We're not quite done. We do need to check this is a minimum. And the way we'll do that is we'll look at the second derivative. So P double dash of X, I'm going to differentiate my expression for P dash of X. So I'm going to get P dash of X equals 4a of x to the minus 3, and at x equals root a, that equals 4a x to the minus 3 on 2, which equals 4 on root a, and that is positive. And P double dash is positive, implies that this is a minimum. All right, we're not quite done, but we're getting really close. Now, we had earlier worked out an expression for theta in terms of a. So theta equals 2a on root a 2 plus root a. I'm just tidying that up as so. I'll get 2 on root a plus 1. Now, let's look at the structure of that. I know that root a is positive. Therefore, I know that 2 over root a is positive, and so when I add it to 1, the denominator is more than 1. Therefore, theta equals 2 divided by a denominator which is more than 1. That implies theta has to be less than 2 as required. And we're done. Thanks for listening to Purple Mountain Maths.